Session we talk about the block diagram algebra. Now we have seen some aspect of this block diagram representation when we expressed the closed loop system by the feedback diagram. Now the objective of doing this representation is that we have seen the different aspects of controller. For example, the proportional control always results in an offset. We can really do that analysis by using the block diagram algebra and finding the dynamics of the process. Similarly, when you say that the PI controller may result in oscillation, how to analyze that theoretically can be done by using the block diagram analysis. And for doing that, we need to understand the fundamental aspects of this block diagram algebra. Now to start with a very simple process that in the block diagram algebra, the process are represented by blocks. So in simply, input and output are represented by simply a block. So input comes in and it transfers the input into output, and that's represented by the transfer function. And we have seen that this transfer function is nothing but these two equation representation are similar in a sense that this is in the Laplace domain and this is in the time domain. Okay. Now we do not represent those signals in the time domain in the block diagram, rather in the Laplace domain. So we'll from now on, we'll not be using any representation in the time domain for these purposes, rather doing the Laplace domain explanation. Now in block diagram algebra, there are two main blocks. One is what is called this multiplier block, and another is what is called this sum block. So multiplier block represents the relation between two signals when they are connected by a transfer function, meaning that we know that the relation between ys and us we express by a transfer function. We typically will use the notation gs to represent in transfer function, and we have this relation ys equals gs us. So in the block diagram, it's simply represented, the transfer function is represented by the block, and the output is the signal coming out, and the input is the signal what is going in. The other block is the sum block. Here the sum block is used to add or subtract different signals. So you see that for this case, ys simply nothing but is the addition of these two signals xs and ds. So this mathematical representation is represented by this sum block. Now the same signal can be represented in different ways. The final result will be the same. So for example, for this case, this signal ms is nothing but the addition of x, y, and z. Okay. Now if you see that this same sum block can be represented as a summation of two sum blocks, meaning that here this signal m1 is nothing but x plus y, and then m is nothing but z plus m1, which eventually becomes x plus y plus z. So you see that for these two cases, they are represented by the same mathematical formulation represented by these two different block diagrams here. A negative addition. So to represent subtraction, we use this negative sign instead of the positive sign. So here in this case, ms equals simply x having a positive sign, y having a negative sign, and z having a negative sign. So it's nothing but xs minus ys minus zs. Okay. The same thing over here. We can have m1 to be x minus y, and then when you subtract zs from there, because that's also negative, you get the same expression. Now in terms of the blocks can also be used interchangeably, meaning for this case we have this signal xs coming in, going through the block g1s, and this resulting signal is going through the block g2s to give the final signal ys. Okay. Now if we have this xs going first through the block G2S and the resulting signal going through the block G1S and resulting the final signal YS, these two are really equivalent. Okay, you can see that both has the end result to be ys equals g1, g2, x, s. Okay, so the blocks can be interchangeably used, meaning that in a block diagram, if the blocks are there, they can be moved in an equivalent way. The other way that if we have a representation something like this one, so here we see that ys equals gs times whatever signal we have here. Okay, now x1s plus x2s, so those are summed together. Whatever is the signal go through gs, we get the ys. Now the same thing can be represented as x1 going through a gs and x2 going through gs, and they sum together to produce ys. So for both cases, we see the end function, this ys, is the same. Now let's do some mathematical manipulation to see what is the expression for ys here. Now ys, you can see I can give a temporary signal name here. So suppose m1. So ys equals, now what is m1? M1 is nothing but these two, summation of these two signals. If I give this to be m2 and this to be m3, so we have m1s equals m2s plus m3s. Okay, now what is m1s? Nothing but x1s times as, so as x1s. And what is m3s? Nothing but cs x2s. Okay, now we get m1s in that case, m2s plus m3s, meaning that plus cs x2s. Okay, now plug in this expression over here, we'll get ys to be, finally I can write ys will be bs at the denominator. I will have as over bs x1s plus cs over bs x2s. This is one of just a simple block diagram algebra preliminaries. Now we see that what can we do for this case. Now let's find out the expression for ys for this case. Now again, ys will be something, if I give the name of the signal somewhere is m1, this one is m2, this one is m3. The same way I can write down ys equals, this is 1 over tau 2s plus 1 times m1s. Now m1s is nothing but m2 plus m3. Now m2s equals x1 times 1 over tau 1s plus 1. And m3 is, so m3s is 2x2s. So if I plug in here m1, which is m2 plus m3, we'll end up getting ys will be m2s is 1 over tau 1s plus 1, and then 1 over tau 2s plus 1. So it will be eventually 1 over tau s plus 1, tau 2s plus 1 times x1s plus 2 over tau 2s plus 1 x2s. So that's the final expression for ys. Now for this part, we see that ys, we can start from the final expression ys equals x6 plus x5. So ys x5s plus x6s. Now we see that x6s is the signal coming here, so it doesn't have any relation with other signals, but x5s is simply g2x, x4s. So we can simply write here g2s, x4s plus x6s. Now what is x4s? x4 is nothing but x2. Here you see that this sign is negative, so x2 minus x3. So we'll write g2s times x2s minus x3s plus x6x. Now we see here x2 is now g1 x1. So we'll write here g2s and x2 is nothing but g1 s x1s, this g2 x3s plus x6x. So that's the final expression for ys. Now let's look at the case where we have some sort of a loop here. How to deal with this case. Okay, now for this case, we'll again follow the same procedure. To start with, say ys equals, we have this signal coming in x6 plus x5. So simply x6s plus x5s. Okay. Now we know that x6 is an external signal coming in. There is no relation with any other signals, but x5s is nothing but g2x x4s. So you have g2x x4s plus x5s. Now x4s is nothing but x2 minus x3. So we'll write g2s x2s minus x3s plus x5s remains there. Sorry, this is x5, this is x6. So this is x6s remains there. Now we see that x2s and x3s together produces x4. Now x2s is also g1x, x1x. Now here x3s is nothing but g3x times this ys. Okay, so we'll have g2s, x2 is nothing but g1s, x1s, and this one x3s is nothing but g3x ys, plus we'll have x6s. Okay, now we see that on the right hand side there is also this ys. Now if you do this mathematical manipulation to bring this to the other side, you will end up getting g2s, g3s. It's negative. When it goes to the other side, it will be positive, and here ys has a coefficient of 1. So 1 plus g2s plus g3s, ys will be on the left hand side. And if you do the simple manipulation, we'll end up getting an expression ys will be g2 g1 over 1 plus g2 g3 ys, sorry, x1s, and then for this term you will have 1 over x6s. So that will be the final expression for ys. Okay. Now let's see how to deal with something like this one. Okay. Now we can follow the same procedure to get the relation between this, what is called this here, x prime s to x set point s. Okay, now that's one way. Now in general, we have a procedure to get it directly. So when you're trying to find out the relation between, say, two signals between x prime and xsp, so you can simply write the relation between x prime s and when there is a loop in between, meaning we have a loop here between this variable, we have a loop. Okay, so the general expression is that to get the relation between this signal and this signal, first on the denominator put all the transfer function between these two signals. So we have here GP, GV, GIP, GC, GM. So put GP, I'll just not writing the S part there for simplicity, GV, GIP, GC, GM, and in the denominator 1 plus all the transfer functions in the loop. So meaning that all the transfer function within the loop. Okay, so that will be this one, this one, this one, this one, and this one. So we have again GP, GV, GIP, GC, GM. Remember that on the denominator this was included and the numerator this was included. Okay, now take a look at this feedback diagram. So if you want to find the relation between y and this set point, what will be the relation? Simply y over set point. So if I simply write it as y set point, so y over y set point will be simply the transfer function between these two signals, so y and y set point, so GP, GC divided by 1 plus all the transfer function within the loop when we have again GP, GC. Okay, so this is the what will be the most commonly used transfer function that we'll be using, and we said that this transfer function between the relation between the y and y set point, it's what is called this closed loop transfer function. So again, the objective of doing this closed loop algebra is to do theoretical analysis of the closed loop response, and we'll see how to do it.